Right. So, if you didn't catch the memo, we're gonna start off by doing each week off of a chapter in this book. So, this week it's on time complexity. Pretty short, so we can just go ahead and scroll through it. I'll just kind of read it off, and then if anything doesn't make sense, once again, don't be afraid to ask at all. Because when me and Sebastian had to read this, I remember it was kind of hard to follow as like someone who is new to all this material. So, so let me go ahead and link this book in case you want to have it open a second monitor. So there's the book, and then we're on page 17 of the book, or like 27 in the PDF. So so basically time complexity is gonna be like one of the most important things in algorithms, and the reason is because like it basically will tell us how fast our program will be able to run, or in other words, how much it will scale based on the size of the input. So a good measurement that I like to use that they'll put later on here is C++ can do like 10 to the fifth operations. So if you have like a nested for loop and you have an array of 10 to the fifth elements, like it would be too slow because you would multiply the you would plug in the 10 to the fifth and you get 10 to the 10th, which exceeds the 10 to the eighth operations that we can do. So, time complexity of an algorithm estimates how much time an algorithm will use for some input. So, here they just give you some basic examples of how time complexity works. So, the way I usually explain it is like the number of for loops is a pretty good indicator of what the time complexity will be. So right here, you have a for loop going from 1 to n, so the time complexity is big O of n, because like if you plug in n into here, it'll kind of tell you how many times you're looping around, right? If n is equal to 100, then you're looping 100 times. If it was equal to like 1,000, it would be 1,000. Time complexity of the next one is n squared, because if n was 100, you loop 100 times on the inside, and then for each of those 100 times, you're doing 100 times on the inside as well. So n squared. If you plug in 100, you get 10 to the fourth, or 10,000 loops in total. So order of magnitude. Oh, this is what I was trying to show you the other day, Jason, but I couldn't find it when I was skimming through. So time complexity doesn't aim exactly to tell us the exact number of times like the code will be executed, but it shows like the order of magnitude, or more so like how our program will scale. Oh my God. Let me, yeah, let me do that as well. Sorry. I'm not sure if you were following along with the book.
That's
Also, you can talk, by the way.
just know that
Uh,
you're being watched.
um, so so if we go through these examples here, a time complexity does not tell us the exact number of times the code in the loop is executed, but shows the order of magnitude. So like I said, like you're not necessarily always gonna know the exact number of operations, but like it's important to know how it scales. So right here, the time complexity of all three of these is still O to the n. Because like, yeah, we're multiplying this by 3, but like in the grand scheme of things, like it doesn't really affect like the magnitude in general. So we multiply this by 3, it's still O to the n. We can add 5, it's still O of n. We can like we increment I by 2, so technically this code would only run n over 2 times. It's still O of n. And then they just give you another example here. This is still O of n, and like instead of starting j at 1, it just starts from I plus 1. So like you have a lot less operations than if j started at 1, but it's still calculated as O of n squared. So in order to get time complexity, we just base it off of like the magnitude. It doesn't matter if like we're doing 2 times n or like something else. We're not trying to get like an exact number. We're just trying to figure out like the order of magnitude, like they say here. Are we all good on that?
It would be safe to say that one for loop is typically always going to be O to the n once you see a nested for loop square it.
Yeah, pretty much. There are some obvious like exceptions, like for example, maybe like what if like on the inside you're like iterating from like j equals 1 to j less than square root of n, well then this would become n times square root n. But like for the most part, if it's n either added or multiplied by some like small constant factor, we don't care about it.
Oh,
There's actually I'll just scroll down to show you like examples of the different time complexities. So you have O of 1, you have log n, you have O of n, and then here's that square root thing I was talking to you about. So square root actually like is like a different like complexity class, I guess is what they'll call it. And it's like important because like if we plug in like 10 to the 8th, we can like it then becomes like 10 to the 4th, which is like significantly faster, like 10,000 times faster. So like it starts to matter then. But if you're just multiplying it by like 5 or something, then it's probably not significant enough to matter. Um let's see, where were we? All right, we're down here. So sometimes the time complexity depends on several factors, so you might not always be like just iterating from like 1 to n, right? You might have multiple variables. So like, a good example is let's say you have like a 2D array and you have n rows and m columns. You're not gonna go to n both times, right? You're gonna have one for loop until n and then the other one until m. In fact, that's kind of like what this code is here. So like you could say what the time complexity of like iterating or like outputting through a 2D array would be O of n times m. They put it right here. Um, Recursion, this is something I actually didn't really understand until recently because it's not really as easy to tell like what the time complexity of your recursive algorithm is because like you don't have it like in for loops, right? Like it's not necessarily as obvious. So so what they say here is the time complexity of a recursive function depends on how many times that function is called, and then the time complexity of each of those calls. So time complexity of this one is still O of n because we have some n, and then we're gonna keep making calls until n is equal to 1, and we're just gonna reduce it by 1 each time. So like if n was equal to 5, we would still only get 5 calls, so like O of n for this one. Um, for this one though, where we have like some value n, but we're calling the function 2 times for each recursive call. So like it's gonna constantly branch out because each one call will make 2 more calls, and then those 2 calls will each make 2 more.
oh,
I think they actually give a diagram, or maybe
so,
they don't. But like it very quickly like branches out, right? So the total time complexity is 2 of n, or 2 to the n, because if we start at g of n, we only have 1 call so far. Then we go to g of n minus 1, we double it, we get to 2 total calls. G of n minus 2, 4, and it's gonna keep going until like we're done. So the total time complexity is 2 to the n.
oh,
I think the binary search contest we did yesterday, there's actually a problem on the Fibonacci sequence, and you could solve it in 2 to the n with actually I have it saved right here. So here's a Geeks for Geeks code on how to calculate the Fibonacci sequence recursively. So you'll notice this is very similar to that code that we have in the book. So what you can see is that the time complexity of this is 2 to the n, which is pretty it's gonna scale really bad, right? So for example, let's say like you were able to calculate the Fibonacci sequence in O of n, which you can do. So if you're calculating like the 1000th Fibonacci number, if it was done in O of n, then we would just have 1000 operations, right? You just plug in the 1000. But if we do 2 to the n, all of a sudden we have to plug in 1000 into 2 to the n, which I'm pretty sure this can't even be shown in Desmos because the number is so big. Actually, no, it can. 10 to the 301st
oh,
calls, which is gonna like obviously like take forever. Like this would take like probably like millions of years or something. I don't know. So the reason the recursive Fibonacci code actually works in that problem is because they don't give you more than like the 20th Fibonacci number. So like you're only gonna have to do this many calls, which is less than 10 to the 8th, which is why we can do it. So
oh,
now they give you all the classes. So O of 1, this is basically constant time. So like it doesn't depend on the input size. You can just straight up directly calculate it. So like an example would be like, let's say like they give you variables and then you plug straight into like a math formula. That would that would usually be O of 1 because like you just like plug the variables into the math formula and it just calculates it. Um, a logarithmic algorithm, it usually like halves the input at each size or at each step, or maybe it's like cutting it like in thirds or something. The point is that like you you're doing something to the uh to the log of like that respect. Most of the time it's gonna be log base 2 in computer science because we're like cutting stuff in half, right? So for example, like binary search, we're uh we're checking the middle and we're either gonna like go to the left of the middle or the right of the middle, and every single time we like do a check, we're gonna cut it in half. So for binary search, since we're cutting the size of like what we're looking through in half every single time, the time complexity of binary search is log base 2 of n. So for
Oh,
example, if we're trying to binary search for an item in an array of size 32, we would do log base 2 of 32, so it would only take 5 loops or steps to find what we want. Linear just refers to O of n. So, for example, like let's say like you have an array of n elements, you got to write a for loop from 1 to n. So the time complexity of like even iterating through an array, so like checking an array or outputting an array or anything, that's going to be linear. So, they say here that it's usually the best time complexity, and the reason is if they give you n elements, how can you possibly like find what the answer is without like actually checking the array itself? So they say this is usually going to be the best time complexity if you're like given an array or something. N log n, really common time complexity if you're sorting. The best sorting algorithms are done in n log n, as they say right here. So your time complexity is gonna be n log n if like you sort and then everything else is like maybe done in O of n or something. Another possibility, let's say you have a data structure that like every operation takes log n. So maybe like a priority queue. Every time you insert into a priority queue or like a set or something, it's got to find where to put it, and that's gonna take log n time. So if you're processing n elements and each element has to be inserted in log n time, total time complexity is going to be n log n. Quadratic, this is just nested for loop, and then I think it's going to start to, the rest of these will start to get repetitive. Cubic, same thing. Let's say you have 3 nested for loops, and it's going to keep going. 2 to the n is usually like, it has to do with generating subsets, because you remember like that one lesson from like maybe a month back, there are 2 to the n total subsets for any given array. So if we want to check all the subsets, it's going to be 2 to the n. N factorial, pretty much never used, but it has to do with permutations or like generating every single permutation of a set. Because n factorial scales really bad, I think you can only like you can only have a n factorial algorithm run if like n is less than 10. So polynomial algorithms, its time complexity is just represented in the form of O of n to the k, where k is just some number or constant. Um, all time complexity, so n squared, n cubed, n to the 7th, anything else, that's going to be polynomial. And those are going to be, in general, a lot faster than your exponential functions, such as like 2 to the n. Because as we can see here, right, like if you plug in something to 2 to the n, you start to get really big numbers really fast. Let's say you're plugging in like 100 for 2 to the n, we're already getting 10 to the 30th. So like our numbers just scale really big when we have exponential time complexity. An NP hard problem is basically just known as a algorithm or as a problem where there's no polynomial algorithm that can possibly solve it. Most of the things we deal with in competitive programming and most of the stuff in the real world is solvable in polynomial time, but there are certain problems where like we can't solve it in no matter how many like for loops we write. Like it can't be solved in like O of n to the 7th. We gotta we got to use some exponential algorithm. So here's some estimations that they give you. Once again, I say that you can do about 10 to the 8th operations in C++. I could have sworn they put it here. You'll usually see it in other books. Maybe I just saw it on a different site, but it's not in here, but they would just give you these estimations. So for n factorial has to be less than 10, n cubed preferably like less than 500, n squared less than or equal to 5,000, and you notice that like if you plug these into Desmos, a lot of these would be around like 10 to the 5th, which is like that guideline. So I think the only thing that's left is just this example. So they give you this problem where you have an array and then your job is to find the maximum subarray sum. So what a subarray is it has to be contiguous, so they have to be consecutive values. So like if it wasn't like consecutive values, then you could simply just take every single positive number. Like you take this, skip over the 3, and then take this 5, take this 2, skip over this -5 and take the 2, but it's got to be consecutive values. So right here, apparently this is the best answer, and it, as you can see, like they're consecutive. It has like a block of 5 in a row, and the solution is to just like subtract 3 from your final answer because like these 5 and 2 values will make up for it later on. So there's a lot of ways that we can solve this, but they're not all equal. Some algorithms will be faster than others, and this is where time complexity is going to come into play. So as they say here, the most straightforward way to solve it is to calculate every single subarray. So you're going to have a loop from a equals 0, a to n, and then b equals a, b to n. So what this is doing is a will represent like your left and a will represent your left and b will represent your right. And then you're gonna loop from k equals a to k equals b, and you're just gonna add all the numbers on that left and right range into your sum. Then you're gonna update your best answer with itself, and then that sum that you find. So by the time you check every single subarray in here, you're going to find your best answer. But the thing about this is you have 3 for loops, right? So time complexity is n cubed, so it's going to be really slow. If we're dealing with 1000 array elements, we couldn't process this in a second. We'd have to like sit there and maybe wait like 10 seconds for it to find out. And like 10,000 isn't really a lot of elements, right? So we can do better. So they give us a nice optimization for the next algorithm. What we're gonna do is instead of like having a left pointer and a right pointer and then making a third for loop to check everything from the left to the right, we're just gonna add it at we're just gonna add that element the same time we declare our endpoint. So they say like we're gonna remove a for loop from it. Calculate the sum the same time when the right end of the subarray moves. So A will still represent our left endpoint, but we're gonna have n be our endpoint, and then we're gonna add A like at each step. Wait, let me see if I'm understanding this right actually. B to A or B equals A all the way into n. Wait, Sebastian, how does this get how does this get like subarrays that don't reach the end? Like how would this get that, for example?
Were you
'Cause
asking me?
yeah, 'cause B still loops until n. I was when I read this earlier and it made sense.
And
Maybe I'm
it's
just
the
missing something.
Okay, wait, which part?
Yeah. So it's just Cadane's algorithm, but like it's just removing a for loop. But they're saying like you just calculate the sum when you move the right end of the subarray. Oh wait, I
It's
see it
an
now. I see it
intermediate
now. Yeah,
step,
never
yeah.
mind. Yeah, I see it. So it's just gonna increment its sum at each step. Whenever you like, so it's gonna increment its b, which will represent your endpoint, and then each time it's just gonna add that last item. So like it already has the sum, it's just gonna add that last element. one at a time. So like let's say you have this, it already has that sum and it's gonna update the maximum, and then it's gonna add this number and update the sum, and then add this number and update the sum, and so on. So that's how this one works. It's a little optimization, but it works in O of n, or not O of n, O of n squared. There is a linear time solution for this problem, which is, as I said to Sebastian, it's known as a famous algorithm called Cadane's algorithm. And what it does is it solves this problem of finding the biggest subarray in O of n time. So basically what you do is you loop from 0 to n, and you observe that there's only two choices. You either can choose the next item to extend your chosen subarray, or you can simply reset and start from there instead. So if I maybe like draw out an example, let's pull up Paint. So let's say we have an array of, I don't know, 5, -3, 4, -7, 4, and then 3. So what we can do is we can start our sum off at 0. Sum is equal to 0. So we can add this 5. So currently we have 5. And then what we're gonna do is we can either choose to extend our current subarray and like kind of extend it like this and take the -3, or we can just ignore the 5 and start a new one from here and then extend that one later on. So what we're gonna do is the observation that Cadane's algorithm makes is we're gonna simply take the maximum between if we take it and if we don't. And the reason is because if our sum is smaller than taking this element alone, then like it's better to just disregard everything on the left and start fresh. So I'll just walk through this example real quick. So our sum is currently 5, and then we're gonna take we can either choose to take the next item or not choose the next item. So this is equal to -3, so we take the max between our current sum and -3, or -3 on itself. So in this case, it would be 5 plus -3 and -3. And then we get 2 and -3, right? So what that means is it's better to take the -3 than to start fresh. So now at this point we have 2, and we can either add the 4, or we can start fresh. Well, why would we want to start fresh? Because like we can just add the 4 and we can get 6. So now we have 6. So is it better to take the -7 and have -1, or start fresh and be at -7? Well, -1 is greater than -7, so we just take the -7, and now we have -1. So now you'll notice we can either take the 4 and be at 3, or we can start fresh and be at 4. Well, 4 is higher than 3, so we're gonna start fresh, ignore all this, and then just start at 4. And then same thing here. We can either start at 3, or we can add 3 into what we have. We'll take the 3 and we'll be at 7. So that's basically like the logic behind like Cadane's algorithm. At each step, you're either choosing to start fresh or add it into what you have. So the code for it's right here. I put a problem on Cody for this. So you can go ahead and implement this in there if you wanted practice, like trying all 3 of these and seeing which ones like work and which ones don't. So just to give you a little chart, they tell you like for some given size n, how long each algorithm takes. So the first algorithm was n cubed, so at n is equal to 10 to the 4th, it's already taking over 10 seconds. The second algorithm's taking 0.1 seconds, and the fastest one is taking 0 seconds. And you'll notice as we put bigger values of n, like let's say 10 to the 7th, this one has taken over 10 seconds, like from long back. Algorithm 2 will start to take more than 10 seconds, but this last one, it still finishes instantly because it's the fastest algorithm. It has a linear time complexity. Yep, and only algorithm 3 is able to process the largest inputs instantly. So that's the end of the chapter. Basically, time complexity is really important because we need to be able to create an algorithm that will process our inputs as fast as possible. So, do we have any concluding questions? Everyone pretty clear on this?
Yeah.
Nice. So for this week, if you hop into the Cody, we're doing contest 15. All these problems are basically based around like you could solve it in unoptimal way, but you're gonna time out, and then there's a faster way to solve it. So as always, maybe give it an hour or so, and then I'll go over all of the solutions to these so that you can see like uh, maybe like a brute force-ish way that like works, but it takes too long, and then we can find an optimization that we can make so that the program finishes fast enough.
Yeah.
Nice.
And also for like logarithmic time complexity, the base of the logarithm doesn't matter, right? Because it will only
It
be off by
doesn't.
a constant factor. Oh,
Exactly. That's a really good point you brought up. So usually we just say log n. We don't really account for for the for what log it
Nice.
actually is. And the reason for that is most of the time it's log base 2, right? Because like the book said, log base 2 is like when you cut something in half like repeatedly. And notice how like if the base was like any bigger, like it would actually be it would be like even faster. So log base 2 is typically what we're handling, but it's also like the worst case scenario. So so most of the time we just denote it as log base n because like you said, it's just some constant factor. It doesn't matter.
oh, okay. Can we get back to trolling now?
Yeah, I'll stop the recording.